Welcome, everyone. My name is Hannah Hawkins, and I am a research product manager here at RENCI. Thank you all for joining us today for our first ever University Research Week webinar, Innovation in the Changing Technology Landscape. This webinar will feature presentations from RENCI researchers detailing their work addressing changing climates in environment, health, and networking research. The webinar is being recorded and it will be shared with all registrants. If at any point you have a question, please feel free to type it into the Q&A box down at the bottom of your screen, and we'll be sure to bring it up during the Q&A session. We're joined today by our presenters, Drs. Ashok Krishnamurthy, Brian Blanton, Saparna Goswami, and Paul Ruth. Our first presenter is Ashok. Dr. Ashok Krishnamurthy is the director of the Renaissance Computing Institute, RENCI, and a research professor of computer science at UNC Chapel Hill. He's also the co-director for Informatics and Data Science, IDSI, at NC Tracks. Krishnamurthy has many years of experience with informatics and data science, including data science cyber infrastructure, medical image analysis, time series data analysis, machine learning, and high-performance computing. Ashok?
Thank you, Hannah. Welcome everybody to this webinar about RENCI and the many interesting research projects that we do. I'll start off by giving you a little bit of an introduction to RENCI and the history behind RENCI before turning it over to my colleagues who will be walking through very specific research projects that we have going. Thank you, Hannah. So this slide really captures what RENCI does in a single slide. You'll see that we work as with both university as well as industry partners. We are an applied research institute. Within the circle or the half circle, you'll see the main areas of expertise within RENCI: data science, computing, networking, software, and visualization. And right at the top, you'll see our current areas of focus, the domain areas in which we are focusing: life sciences, environmental sciences, and social sciences. Finally, at the bottom, you will see the three universities that provide oversight for RENCI, and I'll talk a little bit more about it in the upcoming slides. Next slide, please. So a little bit about the history of RENCI. RENCI, it will be 20 years old next year. It was founded in 2004 as a major collaborative effort between, as I mentioned, UNC Chapel Hill, Duke, and NC State. It included other institutions also in its initial formation. RENCI's vision is actually guided by an oversight board, and the oversight board is composed of the provost and the chief research officers from all three of these universities. In the early days, our goal was to create a hub for collaboration across the many academic institutions and industry in North Carolina to help scientists in different domains drive discoveries using computing. And now our focus is in helping scientists use data science and computing to drive new discoveries. Next slide, please. How does RENCI fit into UNC as a whole? We are a research institute under the Office of the Vice Chancellor for Research. The Office of the Vice Chancellor for Research has oversight of several pan-campus research centers and institutes, which are supposed to have a function that is crosses all the different schools and the college at UNC Chapel Hill, and RENCI is one of them. You can get more information about the Office of the Vice Chancellor for Research if you follow the link that's there. RENCI currently has about 120 employees. We are funded through a portfolio that consists of a certain amount of funding from the state of North Carolina, funding that is returned to us on the basis of research funds that are generated. There's a trust fund that is mainly funded by certain consortia that we manage and run. And finally, the bulk of our funding really comes from sponsored research that federal agencies, as well as other organizations support us. Currently, across RENCI, we have over 60 projects that are ongoing. Next slide, please. So what is it that RENCI wants to do? Our vision is that we want to be a leader in data science, and we want to drive and be a catalyst for discoveries that use data. And we hope that the major research that we help and advance will lead to better health, a safer environment, and an improved business and economic climate in North Carolina and beyond. As a mission, we mainly achieve our vision by developing and deploying data science cyber infrastructure, which are really large computing and network systems to help advance data science. And we work with researchers in academia, government, and businesses to do this. And we use our primary goal is to help these places use data to make new discoveries, make informed decisions, and as I mentioned before, spur economic development. Next slide, please. Thank you so much. I'll turn it over back to Hannah to continue.
Thank you, Ashok, for that overview and history of RENCI. Next up, we have Brian. Dr. Brian Blanton is RENCI's Director of Earth Data Sciences and an oceanographer with 20 plus years of experience in analysis and simulation of the coastal ocean, high performance computing, and earth sciences data analytics. His research usually involves applications of the tide, storm surge, and wind wave model ADCIRC for problems on storm surge and tide dynamics, interaction of storm surge and coastal river flooding, and the impacts of climate change and sea level rise on coastal hazards and risks. He earned a Bachelor of Science in Mathematics from Armstrong State College in Savannah, Georgia in 1991, and a PhD in Marine Sciences from the University of North Carolina at Chapel Hill in 2003. Brian?
Great. Thank you, Hannah. Thank you all for joining. Let me turn off a fan in the background. Sorry. It gets hot in this office with all the computing. So I'm talking today about a project called the ADCIRC Prediction System Visualization and Data Engine. It's a long title, but on behalf of the entire group of Earth Data Sciences here at RENCI and the RENCI Communications Group, which helps us quite a bit with web development activities, and in particular the Coastal Resilience Center and Institute of Marine Sciences, where Dr. Rick Ludick and Shantara Bunya are located, and they're key contributors to this whole enterprise. So next slide. So, I mean, the motivation for a lot of what we do is really, I mean, these are nice visuals of some of the motivations. I mean, hurricanes cause a lot of damage. Port entry and exit for container ships and other navigational issues cause all sort of, issues in terms of, extreme weather. And as climate change, makes its presence even more felt, these kind of concerns become ever more present. The lower right is actually an overtopping of the wall during Hurricane Katrina. Just to say that, it's not just, extreme weather that we're ultimately really interested in. It's really presentation of a bunch of information that we generate, largely driven by hurricane and synoptic storms. And if you look in the future, really compound flooding, climate change, and increases in the buzzword, nuisance flooding that you've heard probably a lot about recently, are things that we're really kind of focused on. So the next slide says that really what we want to be able to do is make predictions about storm surge and provide that information to other entities that can use high resolution, high fidelity information for decision making in near real time. And the near real time imposes quite a lot of constraints on how we compute and more importantly, how we disseminate that information, because the results have to be available really as soon as possible. One way to think about it is the forecast cycle from the Weather Service is about 6 hours long. So every 6 hours, they publish a new forecast for the weather, whether it's hurricanes or other types of large-scale meteorological weather. And if we have information we want to attach to that forecast somehow, if it takes us longer than 6 hours to compute our results, then they're already late, they're already old. So we really have to be within that 6 hour window for the results to be sort of most impactful. A couple of pictures here of some flooding during Hurricane Harvey in Houston in the upper right, down to the RENCO storm protection business, which is apparently underwater, which is kind of a funny picture in a lot of ways, but says all of these areas which were historically perhaps not as impacted by things like nuisance flooding or even, moderate extratropical storms are certainly becoming more so in the context of hurricanes and climate change, for example. Next slide. Need to speed up here a little bit. So the major challenges really in predicting coastal hazards, in particular storm surge, in very detailed ways, really has to do with the complexity of the physics of water being pushed toward the shore and then interacting with the physical environment, for instance, levees or even roadway beds, and how that entire mechanism affects ultimately things like people and damage and other more social data or social forces, if you will. So there's a lot of scales that have to be sort of dealt with in terms of physical scales. It's very important to couple the storm surge model to a wind wave model rather, that helps simulate what the wind-driven waves look like, because that can be very important. There are also computational challenges. If you want to do this at very high resolution, you need sort of big computers. It generates a lot of data. And you really need, again, to be able to compute and make available information in as close to real time as possible for it to be super useful. A couple of figures here, a big high performance computing machine. This is not the one at RENCI. And then the little triangle grid in the lower right is what a model grid actually looks like. It's formed with triangles instead of squares, and I'll speak to that in just a minute. And all these slides are available, after the fact, because there's kind of a lot of information to go through, and we can come back to it. But basically, the next slide says that one of the tools that we like to use, or that we use in this particular environment, is a model called ADCIRC, which has historically been developed both at UNC and Notre Dame by Rick Ludick and collaborators. And the bottom line is that this is a computer model that solves the old, Newton's F equal ma, but obviously not just in that form. It's formulated for thin fluids, meaning oceans, on a rotating sphere, which is Earth, and then we need large clusters for efficient and effective real-time communication. That model is encapsulated or wrapped in something called the ADCIRC prediction system. And you can think of the ADCIRC prediction system in the lower left here as a big piece of software that manages collecting weather, tidal information, other data sources, making them available to the ADCIRC model, and then ultimately dealing with the output from that model in a variety of different ways. This is actually what a big ADCIRC grid looks like for the entire East Coast and Gulf of Mexico. It's a triangular-based model, so what you see are triangles, and where you don't see triangles, where you see a lot of gray, means it's very high resolution. And that very high resolution imposes computational costs. So the next slide will say, at the end of the day, though, we need to be able to show this information to people. So we've developed something called the APS Viz system or user interface, which is a cloud-based visualizer for the ADCIRC prediction system. And it is a web page, ultimately, that hosts geospatial information like maps of the storm surge that you see here, additional information like hurricanes and the tracks and their intensities. And then you can drill down into the data by clicking on one of those dots, and you get information about the time-dependent nature of the solution there. And this is actually not necessarily at a time when there's a lot of action on the coast, right? Because the hurricane hasn't reached the coast. This happens to be Hurricane Lee from earlier this year. But the point is that it accumulates this information and makes it available in a pretty intuitive website that helps others and us understand what's going on in these simulations, so that we can talk about them with potential end users. So this is what the website looks like. The question is, how does this get built, given the fact that the ADCIRC model is kind of complicated? So the next slide starts to get into this. So the ADCIRC prediction system on the left generates information on high performance computers using the ADCIRC model. It feeds the data into basically a big repository for information. And this pyramid structure really is meant to convey that ADCIRC is the bottom lower level technology. And it is a sophisticated model. It's been around for a while, and it's got a lot of nice features. But it's been there. It's been there in development for the last 20 or so years. Above that sits the manager for ADCIRC on something like a high performance computing system. Above that is really what we're calling APS Viz, and it says Kubernetes here. So it's the thing that manages turning the AdCirc information in its native format into something that can be visualized and made available to others. At the end of the day, what happens is there's an arrow out here to the right where all this information gets pushed so to various types of endpoints like S3 buckets, GeoServer, GeoServers, and Threads databases, so that external clients like FEMA or various departments of transportation can get that data and then stick it into their development platforms or their decision-making platforms. So the next slide goes into a little bit about the technology. So all of that layer that was labeled Kubernetes manages a whole suite of containers, Docker containers, that push the data around and convert it from one format to another so that it ultimately is sort of web ready. This is just a list of the technologies that are sort of embedded and running around in various levels. I would say the most important really, Teria is the web mapping framework that we're using to build the website itself. It's very interesting. It's an open source product out of Australia. Kubernetes is the system that manages all of the stuff going on our big Kubernetes cluster downstairs, but it turns out that it is immediately deployable to Amazon Web Services. So we actually have both systems running at the same time. And Amazon, of course, is a great way of offloading cost or really getting an institute like RENCI out of the critical path in real time, right? And if RENCI went down and we had no other way of getting information out, then we would be stuck. So relying on sort of cloud-ready resources like that is pretty critical. The next slide will get into what does the workflow actually look like. Now, there's a lot on this slide, and you don't have to look at any of it, except realize that there's a lot, right? So the concept, what the Kubernetes supervisor does is it manages and creates a whole bunch of processes that allow us to go from the AdCirc model all the way to the website. And there's containers, there's processing running around. So the next slide will say sort of the following. It's going to say what we talked about earlier, AdCirc on one end and the website on the other are these two boxes, and everything in between is essentially managed by this Kubernetes supervisor process, simply to make the data available to a website or to some other end user. Now, I mean, I'm being a little bit facetious and quick about that, but only to say it is really complicated because there's a lot of stuff that has to go on. And again, the point of this is really just to give you an idea of what this problem is about and the solution that we actually took, or the path that we took to get that. It's really important for error handling, or that this system does things like error handling, because at the end of the day, the website kind of has to function, and it has to have data available that has been sort of vetted by experts and such. And so this whole enterprise is really set up to manage this entire problem. So the next slide will then get into end users. What are people actually doing with this data? Aside from our own website that I showed a snapshot of earlier, we realized that the information that we derive in this middle layer called Kubernetes is actually maybe just as important for other people as it is for us to be able to put it on our website and say, look, there it is. So I'll just show a quick example here of this sort of cloudy thing over here is where all the data gets housed on various types of servers to serve different end user needs. And we have a variety of end users at the moment that are getting data out of this entire infrastructure to do something with. So I'll show you two quick examples of that. So on the next slide, North Carolina Department of Transportation has several applications that they run in real time, sort of critical crisis situations, if you will, to alert them to things like potential roadway closures or even bridge failures, which is actually a lot less likely to happen than road closures. But the point is that they need real-time information in high resolution. They have a lot of data that comes in from various sensors. So something like BridgeWatch actually accumulates all of that information together. What they were very interested in is high resolution predictions of what would happen to water sloshing up onto land and eventually, potentially causing road closures and bridge damage. So they're ingesting our information in AdCirc Viz out of that layer with the little cloud up there, and sucking it directly into their transportation analysis codes. And it's been a very interesting discussion with them, because they are I mean, they're not AdCirc experts at all, but they do know a fair amount about storm surge. And then, of course, they know a lot about transportation. And so it's been a very interesting way of bringing essentially a state agency together with some key operational applications of a lot of our research on the AdCirc in the storm surge world together. This graphic is actually a composite of several different of these tools, so it's not just one tool. But what happens in this upper right-hand panel here is in real time, as they ingest our information, it will pop up little warnings that suggest to DOT here are areas that you need to be concerned about in terms of road closures. In the next slide is another example of a different collaborator with a very different end goal. We partner with the Water Institute of the Gulf, which is building an entire new flood identification and warning system called Flood ID. And their big concern in the Gulf of Mexico is obviously hurricanes. So they wanted to develop a website, but what they didn't want to do necessarily is develop all the information that goes into the website. So we partnered with them and basically provide access through our little cloud layer over here to all of the information that we compute. And they can pull that out in a very, web services driven way and populate their own website for their own end users, which in this case is the state of Louisiana. This is a test simulation that we did a couple of early summer from Hurricane Ida as it makes landfall in the Louisiana area. And this is the high water, or the storm surge essentially, being caused by that storm displayed on their website. So I've talked a lot about things being displayed on websites. It turns out that what you can't see in this upper left of their web page here is that all of this data is connected to decision-making dashboards, some of which has to do with positioning resources for post-storm activities, post-event activities, meaning getting water to people basically. And so these dashboards connect to their data ingest system using some of our data to make some of their decisions in real time. So the whole point of this was really to just give an overview of a pretty complicated problem, how it goes from the core, physics solver AdCirc all the way down to end users or all the way up to end users, and how they can use some of this information in real time to service things that we're not even thinking about. People, decision making and in the context of evacuation routes and things like that are. We're not focused on that. We're focused on computing the surge or the hazard and then getting it to people that can do other things with it. I believe that is the last slide. Yes.
It is indeed. Thank you so much, Brian, for that fantastic overview. Next up, we have Suparna. Dr. Suparna Goswami is a senior research scientist at RENCI and a co-lead of the Community Data Standards and Knowledge Graph Search Group for the NIH HEAL Data Stewardship Group. Goswami has several years of research experience in the areas of innovation management, user experience research, quantitative research methods, and in leading interdisciplinary multi-institutional research projects. In addition to her academic background, Goswami has years of industry experience in the development and implementation of large-scale multi-organizational information technology systems. She has published in premium journals and conferences in the areas of information systems management and computer-human interaction. Suparna?
Yeah, thank you, Hannah, for the introduction. And after Brian's very interesting talk on what RENCI is doing in the domain of earth sciences, I will today present to you, next slide, please, a project or a tool that RENCI, along with our partners RTI International, have developed in order to facilitate, that covers the domains of data science in the context of life sciences research, and more specifically, like the domain of biomedical research. So today I'll be talking about DUG, which is a semantic search tool, which was developed by RENCI and RTI International. It is currently being deployed in two large projects funded projects in the areas of biomedical research. One is the NIH HEAL initiative, and the other is Biodata Catalyst, which is funded by the NHLBI, the National Heart, Lung, and Blood Institute. Next slide, please. So I use HEAL as the example in which we will, the context within which Doug was deployed. So first of all, what is HEAL? HEAL is NIH's ambitious initiative to help end addiction long-term. And it has two primary areas of focus. One is understanding and managing and treating pain without the use of opioids. And the second is improving prevention and treatment of opioid addiction, which we are aware is like one of the major reasons or sources of death in the US. And HEAL is huge and diverse. So currently there are projects funded in all 50 states with $2.5 billion in research funding by NIH. There are more than 1,000 awards that have been made so far, different research programs, and it has been ongoing since 2018. Next slide, please. And as I mentioned, the HEAL research landscape, not just in terms of the money being spent, in terms of the geographical coverage of the HEAL initiative, it is huge and diverse also in terms of the different areas of research that is being covered, the different data types that or the data types of data that is being generated by the HEAL awards. So for example, the awards funded by the HEAL program are funding translational research, clinical studies, basic science research, therapeutics and drug development, and social and behavioral research. And these research projects are generating a variety of data, such as which covers health records, behavioral data, imaging data, demographic information, public records, genetics, and all sorts of omics-related data, just as proteomics, genomics, metabolomics, and so on and so forth. So essentially, so on one hand, we have different types of projects, different types of studies, and these data and these studies are generating huge volumes of data. And here, the question or concern is not, challenge is not of a scarcity of data, but rather an abundance of data, and how to make the best return on investment from the huge amount of money that is being spent by NIH and the federal government, and how to kind of allow people to discover knowledge and make best use of the data that is being generated by the HEAL program. Next slide, please. So what RENCI's role in this HEAL initiative is, we are the HEAL data stewards. So in addition to the awards that are being funded by NIH, there is a HEAL data ecosystem, which is part of the HEAL initiative to address all the data related needs for the HEAL initiative. And the HEAL ecosystem, data ecosystem, works very closely hand in hand with the different stakeholders, particularly like the researchers, clinicians, and other communities and other stakeholders, and with NIH in terms of figuring out the best practices, the standards for data collection, for data storage, data reuse, and so on. And one thing to keep in mind is most of this data are from like patients and human subjects, although I mean there is a lot of basic science or research that is being done in order to generate, come up with new drugs or animal model studies. However, a bulk of the here awards are actually dealing with patients, human beings, and generating data, which makes it particularly complex in terms of handling all sorts of privacy and ethics related considerations of how this data can be stored, who can it be shared with, and who can use that data, and so on. And in order to address all these challenges, NIH funded the HEAL data ecosystem, of which RENCI is the major part. Next slide, please, Hannah. Yeah, so the HEAL data ecosystem's goal or mandate is to accelerate sharing of HEAL generated data and results among the various stakeholders of the HEAL research landscape. And the goal of this program, or the goal of the HEAL data ecosystem, is to enable new discoveries by ensuring that HEAL data can be searched and analyzed. And so in essence, what the HEAL data ecosystem, and in particular the HEAL data stewards, which is us at RENCI and RTI International, what we are doing is we are trying to facilitate open science through making the HEAL-generated data fair, meaning findable, accessible, interoperable, and reusable. Next slide, please. And how do we do it? So first of all, it's important to understand that HEAL, like this 1,000 plus awards that are generating data and different types of data, it's a federated system. There is no one repository where all this data will be stored. These are different research programs spread across the country. They are storing their data in different repositories based on the unique needs and characteristics of the study and of the data that they are generating. For example, human data or clinical trials data is stored in some repository. Animal model data might be stored in something else. So there are several repositories within which the data is getting stored. And again, based on the nature of the data, these data have extremely stringent privacy and security considerations. So these are the two constraints or two characteristics that define the nature of the tools and technologies that are needed in order to make this data fair or findable, accessible, reusable, and interoperable. Next slide, please. So the problem is NIH's mission or goal is how to make this data accessible and reusable. And here the problem statement, getting down more into the details, is how do we allow researchers or the general public or stakeholders to search for and make connections between HEAL studies. This is a challenging domain in which we need to come up with solutions that help enable users to accomplish this task of making connections between HEAL studies so that they know who are the other people who are doing similar kind of research. Can different research studies or data sets generated from different studies be combined in order to do some sort of secondary or meta-analysis? And what can we already learn from data that has already been collected rather than reinventing the wheel and generating a similar data set over and over? And our proposed solution is a tool for searching across studies without actual data access or even knowing specifically exact keywords. So a user can search through the data, find out connections between data sets without seeing the data, without accessing the data, and even being, even not knowing the exact keywords that they need to search for. Next slide, please. So, and for that, RENCI developed DUG, which is a semantic search engine. RENCI, along with our partners, RTI International, developed DUG as a tool that can help researchers in accomplishing some of the goals of facilitating open science. And what DUG does, it helps users search for and delve deeper into biomedical concepts by surfacing related concepts, studies, and variables. It helps users identify data sets and variables of interest to researchers and therefore opens up opportunities for secondary and meta-analysis and knowledge discovery, new hypothesis generation, and testing of those hypotheses. Next slide, please. Now, what do we mean by semantic search? We mentioned DUG is a semantic search engine. So semantic search essentially denotes search with meaning. So the search results are enhanced by incorporating knowledge about the biomedical concept or about the term that is being searched for, by looking up synonyms for their terms, and by finding relationships among different concepts to each other. And what are these concepts? So biomedical concepts could be a biological process, it could be a chemical entity, it could be some anatomical entity, a disease or gene. For example, like a disease could be heart attack. And a synonym for heart attack is myocardial infarction. So DUG will know that heart attack and myocardial infarction are one and the same. And if a user searches for heart attack, the DUG semantic search tool will know that the user would also like to see studies which haven't really used the term heart attack, but have talked about myocardial infarction. Similarly, it might, the Doug search tool will also know that arrhythmia is something that might interest the user who is searching for heart attack, because arrhythmia has, is related to heart, and it has relationship, it is conceptually related to heart attack. And in the same way, it might know there are chemicals, medications, drugs that are related, that are used for managing or treating heart attack, or for that matter, any other disease. So this is what a semantic search engine, and in this specific case, our tool, Doug, knows and how it works. Next slide, please. So how is Doug implemented? Without going into too much details, so there are two main ways that Doug works. The first step is it connects concepts to one another, and it does so by using the Robocop knowledge graph, which is again an open source knowledge graph for biomedical concepts that is developed by RENCI. And it integrates information from multiple biomedical ontologies, such as the human phenotype ontology, Uberon anatomy ontology, Mondo disease ontology. So it uses well-established sources of knowledge, which are these ontologies, and it uses the Robocop knowledge graph to know, what are synonyms for certain biomedical concepts, what are, how are concepts related to each other, and so on. And in addition to this component, the second part of Doug, actually that of connecting concepts to studies and variables. And by this, when I talk about studies, I am referring to the HEAL awards or the HEAL studies that are generating data and the variables that these studies are measuring. So it uses a named entity recognition to identify biomedical concepts in the descriptions, in the variable names, and their permissible values of the study. And this information is obtained from the variable level metadata files or the data dictionary files of the HEAL studies. Next slide, please. So this is more of a pictorial visualization of how Doug works, or what are the components of Doug. So on the top, you see top left corner, these are the VLMD or metadata files, data dictionary files that we obtain from the HEAL studies. And this would contain all information regarding the data that is being collected. Well, not the actual data, but what are the variables being measured? What are the descriptions of these variables? How these variables are being measured? Whether they if it is a survey item, what is the questionnaire text, and so on. And it uses the Robocop knowledge graph. Now, using these two sources of information, what Doug does, it looks for concepts and their synonyms in the variable level metadata or VLMD files that we obtain from the HEAL studies. And once it is able to find the biomedical concepts, it annotates this information and stores it internally in a database. And then once the user performs a search, for example, if the user search for muscle pain, it looks it up in the database and it finds not just muscle pain, but all other concepts that might be related to muscle pain, using again, because it already knows that, muscle pain has the concepts that are related to muscle pain. For example, it's a chronic pain disorder or a phenotype of muscle pain, and it presents this information to the user. Next slide, please. Yeah, so this is an example of what the Doug or the HEAL semantic search engine looks like. For example, if you search for opioid use, you will get many concepts that Doug was able to identify as related to opioid use. For example, opiate dependence, which is a type of the phenotype disease, is related to opioid use, and there is a description or overview of what this concept is about. And then there are studies that are related to, and by related, I mean there are studies, HEAL and non-HEAL studies, which have studied opiate dependence. And there are other information pertaining to this particular concept that Doug was able to find and show it to users. And how does it help users in making connections? So users are able to see, multiple studies, for example, in opioid use is related to alcohol abuse, and there might be like 13 studies which have studied alcohol abuse. So a user, a researcher is able to say, okay, these are the studies which might be of interest to me. Let me go in and look further into the studies, see what variables that they have studied, and then further, go further into establishing these connections from there. Next slide, please. Yes, so that is all that I had in terms of DUG and how it supports NIH's mission of promoting and facilitating open science in the domain of pain and addiction research. And if you want to learn more, please explore HEAL, and we will be very happy to give you a guided tour or demonstration of DUG and talk to you more about how DUG is doing its search and what it is doing. So please feel free to reach out to us. Thank you so much.
Thank you so much, Suparna, for introducing us to DUG and to the NIH HEAL initiative. Next up, we have Paul. Dr. Paul Ruth is an assistant director of RENCI's Network Research and Infrastructure Group, or NREG, and is a member of the leadership team for the NSF Fabric Mid-Scale Research Infrastructure Project. He has 10 plus years of experience as a primary contributor to several NSF networking and cloud testbeds, including Genie, Chameleon Cloud, and Fabric. His research interests include designing and developing next-generation cyber infrastructure, supporting high-performance and distributed domain science applications. He earned a PhD in computer science from Purdue University in 2007. Paul?
Hey, thank you, Hannah. So now we're going to go a little bit lower level than what Suparna and Brian were talking about, and talk about how RENCI supports lots of science, domain science, by providing infrastructure for all of this technology to run on. So today we're going to talk about a project that we're working on at Fabric, or at RENCI, called Fabric. It's an NSF mid-scale RI1 project, and we'll get into it. Go to my next slide. Yeah. So Fabric is an NSF mid-scale research infrastructure that empowers researchers to securely prototype and validate highly disruptive network designs in an environment that closely emulates the real systems that computational scientists and domain scientists and data scientists use on their daily basis. So you can think of Fabric as a scientific instrument or a laboratory that enables experimentation with new paradigms of distributed applications and protocols that run both across the internet, but also within the internet itself, within the network itself. So next slide. So Fabric was funded by the NSF in 2019. Like I said, it was an NSF mid-scale RI1 project. That means it was a $20 million project to build Fabric. We just completed the construction phase of Fabric and have transitioned to an operations grant that has funded us for the next 4 years, and probably will get more, and it'll continue after that. But we're good for the next 4 years. So if you want to use Fabric, you have at least 4 years to use it. The large group that runs Fabric, you'll see on the next slide that there's a map that shows the scale of Fabric. We have lots of people that contribute to it. The primary contributors, or the primary people, are RENCI. So Ilya Baldin is the PI of the whole project. Several of us on the leadership team are from RENCI. We also have people on the leadership team from University of Kentucky, Clemson, University of Illinois, and the Department of Energy Sciences Network, as well as a bunch of other contributions, institutes that contribute, and smaller levels, more regional levels. So next slide. So here's the map, kind of like what Brian said. You just want to see the scale of things from the slide. That's primarily what you want to see here, is that the scale of Fabric. So Fabric has a worldwide footprint. It has 33 locations interconnected by dedicated network capacity. That's at 100 gigabits per second for the links on this map that are shown in blue. And the links on this map that are shown in yellow are 1.2 terabits per second. So it's really hard to wrap your head around how fast that is, but it's really production scale like the internet. Each location is a small cloud where experimenters can deploy private routers and switches alongside traditional compute and storage, augmented with advanced accelerators like GPUs and FPGAs and programmable network cards. These user-controlled in-network computational resources are connected with the dedicated circuits between the sites and dedicated to the user during their experiment that they're running. You can think of Fabric as a research cloud that provides low-level programmable network resources in the core of the wide area network. So it's like a cloud, but it's giving the network pieces across the wide area, which is really interesting. So beyond just the US, Fabric has an international footprint. We have sites at CERN, where the Large Hadron Collider is, University of Bristol, where they have a smart cities testbed, University of Amsterdam, which is kind of the center for, or one of the centers for research networking in Europe, and the University of Tokyo, where they do a lot of studies on 5G networking. We also have connections to South America via AmLite and Florida International University. And these international efforts are actually funded by a separate NSF grant called RENCI, which is called Fabric Across Borders, or also referred to as FAB. I might say that, or you might see it in the slides later on. Notably, Fabric partners with Internet2 to offer users the ability to connect their experiments directly to public clouds, such as Amazon Web Services, Microsoft Azure, Google Cloud, through their Cloud Connect service. There's also many additional sites that Fabric connects to. You can see lots of universities listed on this website. We can also connect to other universities that don't have Fabric sites directly. If you're interested in having your university connected, just come ask us. We can do it. Also interesting from this slide is all of the orange stars on here are different, usually NSF funded, but sometimes DOE funded supercomputing centers, as well as other mid-scale test beds and infrastructure that scientists typically use. So this allows the experimenters to use both the real systems they actually use today and connect them with the experimental Fabric networks. So next slide. How do I get to the next slide? Okay. As I've already pointed out, Fabric connects many of the real facilities and services that we all use for scientific computing and data science with user programmable networks. But this is really just an evolution. So the foundational tools of scientific computing the foundational tool of scientific computing is to connect these facilities together with dedicated networks. Like today's scientific computing is totally dependent on high performance networks for a lot of traditional tasks, such as staging data and transfer between compute facilities, or transferring to and from data repositories to compute facilities, and or transferring to and from scientific instruments to the compute facilities, or moving data to the cloud or a campus or some other computing facility. And increasingly, these networks are being used to pull streams of data directly from scientific instruments, such as the Large Hadron Collider at CERN, where we're seeing cryo-EM microscopes that are pretty popular at universities these days, and people are wanting to connect those microscopes directly to networks. At the same time, it's becoming more common for scientific users to integrate a whole lot of facilities, multiple facilities, into a single application, such as advanced computational workflows that involve several stages that ingest data, process data, and then distribute that data. I mean, sometimes these workflows control remote instruments, like the cryo-EM microscopes I talked about, or even use like edge computing to do widely distributed federated learning using GPUs to do AI and that kind of thing. So next slide. Much of what we just talked about is what scientific computing users can accomplish today, but it's a result of huge investment into lots of decades of investment into computational facilities all around the world. These include traditional compute centers with large clusters and advanced workload managers, as well as more modern resources and tools that are response to specific community needs. Like, for example, you might have used Globus to transfer data between some of the computational sites. And there's opportunities that are enabled by new underlying technologies. For example, clouds have really transformed the way loosely coupled scientific computing is performed today. When Brian even mentioned earlier that he's using AdCirc on Amazon, which I think wasn't even true 10 years ago when I was last looking at what Brian was doing. And science team Zs have greatly increased the speed and efficiency of data being transferred to and from campuses, bringing campus performance on par with dedicated data transfer nodes of the large computational centers. Next slide, please. So all of these tools are great, and all of the science is great, but the reality is the reality of the internet is that routers are still only designed to store and forward packets. I mean, this hasn't changed for decades. So applications are still limited to running only on the edge of the internet, and protocols can only be optimized from the edge of the internet. There's a growing emphasis on this edge core cloud paradigm, where applications run across multiple facilities and platforms, and even within the core of the network. Currently, end-to-end performance is achieved through dedicated circuits. Like if you have access to Internet 2's AL2S system or optimized data transfer nodes or SIMS DMZs, you can get access to some performance, but you're still optimizing only from the edge. And the growing footprint of the distributed data and compute means we really need to scale up and re-optimize the systems with the data transfer nodes and SIMS DMZs in the core of the network to have a lot of this functionality at more distributed points within the network. So another way to view this is that there are processing capabilities in all these instruments and data centers and public clouds and campuses. They all exist there and they've been there for a while and people use them, but we don't have them in the core of the network. And this is a limitation imposed on all of us. So next slide. So we have this interesting quote that probably wasn't said by Henry Ford, but it is often attributed to him. And he of course, designed cars and mass production. And he said, if he had asked people what they wanted, they would have said faster horses. And next slide. We see the internet as being kind of in the same place. If you ask scientists what they want out of the network, they're probably going to say faster networks. But we think we're at an inflection point similar to the 1990s when the internet was just becoming popular, and it was making it really super simple to share data via the web. Back then it would have been really difficult to predict all the uses of HTTP and the web that we have today. And we think that smart programmable cyber infrastructure connecting scientific compute facilities, public clouds, campuses, instruments is an opportunity to rethink how the core of the network is used and develop new layers of software that make it possible to deploy applications across the edge in the core in the cloud or the edge and fabric in the cloud. So next slide, please. So towards this goal, Fabric allows users and experimenters to run applications anywhere at the edge, the cloud, or in places where routers and switches are typically found today. This enables in-network processing, intelligent caching of data, distributed artificial intelligence, many other uses that are difficult to predict at this time, but soon might be commonplace. So in addition, Fabric scales both in geographic size, like we're all over the world, mostly in the US, but we're expanding, but also in its performance capabilities. So we mentioned that Fabric has 33 sites connected with mostly 100 gigabit per second or more layer 1 circuits. Fabric also connects or will connect all the real facilities that we already use today, such as the NSF clouds and other test beds, the Access compute clusters, various campus infrastructure. I mean, if your campus or facility is connected to Fabric, you can deploy experiments between your facility and any other facility connected to Fabric. So Fabric's not intended to replace your existing infrastructure. If you use AL2S today or Amazon Direct Connect system today, we're not going to replace that. Instead, it's meant to be a powerful sandbox for experimentation that minimizes security risks and disruptions to your production environment. It's an infrastructure as software, which enables really rapid test cycles with automated redesign for you can experiment with how to deploy your applications across the network and within the network. The sandbox power comes from the real high-performance, low-level dedicated network connections across the wide area, combined with advanced in-network compute storage and accelerators, such as GPUs and FPGAs and programmable NICs that we have in all of our sites. And further, it enables realistic experimentation by connecting directly to the user's existing edge facilities with smart programmable core across the wide area network. So that's the real power of it all. So next slide, please. So what does this mean for, what impact will this have on cyber infrastructure? Well, the next generation of scientific computing will be unbound to any specific compute resources. Applications will run natively across platforms and domains, while including smart in-network processing and computing. We expect the current and future Fabric users, potentially like you, to produce the next generation of these novel in-network applications before these capabilities are commonly available on research and education networks. Additionally, Fabric enables users to produce tools that simplify the deployment of this type of application throughout the edge core in the cloud, especially those tools that are used for managing these large scientific workflows. So it'd be pretty complicated. Beyond producing experimental tools for applications, one of the huge value of Fabric is that it can be used for validation of full-scale prototypes that use really disruptive technologies. So many times risky and or expensive ideas never really see the light of day. This is especially true if the idea requires disruptive changes to the core of a wide area network. So Fabric enables the deployments of prototypes at scale in a secure sandbox while connected to the real production facilities you're using. So this allows you to, this measured validation of these prototypes can be used to justify the effort and money spent on transitioning these prototypes to the production environment. So that's a really powerful thing that Fabric will enable. The ability to operate and take full advantage of these high bandwidth wide area networks is a sought after yet rare skill in academic environments. Like many people that work for Internet 2 or ESNet have these skills, but they didn't learn these from a book or in a virtualized environment or a classroom. They mostly learned these skills once they got a job and they got to touch the real switches and play with them and make them work. And a lot of times they were doing this in a production environment where they broke things. So Fabric allows you to experiment with these wide area technologies at scale in a secure place and potentially do it in a classroom setting before you even get to the workplace. So this is really powerful. Next slide, please. Okay, so typically when I do a presentation like this, I have a much longer presentation. I have a whole list of examples. This particular talk was supposed to be about climate. So I picked out of the many Fabric use cases that we have, users that use Fabric. I picked out the one that was most related to climate, and I'm going to share that with you now. So next slide. So this is a typical Fabric experiment. Like it's not it's not related to climate necessarily. It's just a high level overview. And the idea is that you can deploy inside of Fabric at various sites all sorts of interesting pieces of your application that might be acting as routers or switches, but they might be caching data, it might be monitoring their system, or might be places where other users can subscribe to the outputs of your experiment, that kind of thing. And they're connected to all of the real facilities you might use. And here's a set of examples of facilities that we can connect to. In here we have Chameleon and Cloud Lab and Microsoft Azure and AWS. And I added in here UNC, because if you wanted to connect to something at UNC, we can make that happen. And then over here is just your collaborators institution. So if you have another institution that we can connect to, we will connect to them for you. And you can deploy your application across our facility. So next slide. So what we have is in this particular example, there's a group that is doing climate predictability and forecasting. They're partly at University of Miami and partly at Clemson. At University of Miami, we have Ben Kirkman, who is an atmospheric scientist who studies all sorts of atmospheric science. He is the director of a NOAA center at University of Miami, and he works with Dr. Leo Sequeira, who is another scientist working on atmospheric science, who has ties to Brazil and an organization in Brazil called CP Tech, which is a weather forecasting, a center for weather forecast and climate studies in Brazil. And between Dr. Kirkman and Sequeira, they work with Brazilians and people in Florida to do things to predict climate. They're working with Casey Wang and his student Ben Formby at Clemson. So Casey and Ben are computer scientists doing network research, and Dr. Kirkman and Sequeira are climate scientists doing climate research, and they're working together to try to make the climate applications run more efficiently and better and get more science out of them. And doing this across these wide areas. So that's what we're doing. That's the interesting thing, is we can create these collaborations. So next slide, please. So I don't know a huge amount about this application, except that they're doing climate modeling and they're using Fabric. They're doing something that has to do with forecasting El Niños, and they collect a lot of data. They do it at CP Tech and in Miami. They do the same thing. Everyone has the same problem. If they collect a bunch of data from instruments, they have to transfer that data to the computational centers, chomp on it for a while, and then disseminate the results to the other scientists that are interested in the output. And that's what they're doing using Fabric related to El Nino forecasting. So next slide, please. And what they've done is they've used a portion of Fabric to connect University of Miami and Florida International University and Clemson with Fabric resources that they've deployed strategically throughout Fabric. They're also connected to the Chameleon NSF cloud testbeds where they can get a bunch of cloud, like NSF-sponsored cloud resources and Amazon AWS. And they have links that go to Sao Paulo, to CP Tech to ingest the data from Brazil. And they have some preliminary results where they show that they can go faster using some of their Fabric techniques and some of their caching of data inside the network. And what they really like about Fabric is the clean, measurable environment, so they can run their tests multiple times and get repeatability out of it, and actually see that the effect was their protocols and algorithms, and it wasn't just that lots of people wanted to watch Netflix on a Tuesday night. So they can with Fabric they can get clean, repeatable experimentation, which is nice. Okay, next slide, please. This is wrapping up a little bit. So if you're interested in Fabric, if you have an application you think would run well on Fabric, if you have a facility you would like to connect to Fabric, you can contact us. If you want a Fabric account, you can go to portal.fabrictestbed.net. If you wanted to come to one of our workshops, then we have them twice a year, spring and fall. The next one is at UCSD in spring. We still haven't figured out the exact dates yet, but watch out for that. If you want to collaborate or add your hardware or conduct experiments, talk to us. And next slide, I think it just says thank you and has some more links. So, Hannah.
All right. Thank you so much, Paul, for that intro into Fabric. All right. And thank you to all of our presenters, Ashok, Brian, Saparna, and Paul. If everyone will go ahead and turn on their cameras, we are going to stop screen sharing and we will begin our Q&A session. So our first question is for Ashok. How would I engage with RENCI if I were interested in working with RENCI?
Thank you so much for that question. There are multiple ways that you can work with people at RENCI. If you know of a particular researcher or staff member that you want to collaborate with, I would suggest you get in touch with them directly, and they will be then able to work with you and see what is possible and what is not possible. You can also always get in touch with the leadership at RENCI, which consists of what's called the Office of the Director, and we have an email which is ood@renci.org, and you can email that and ask for express your interest in working with RENCI and what you need to do. So those are two easy ways. I'm going to ask Jeshri. Jeshri, is there a way, another way that people can get in touch with RENCI folks to collaborate? Maybe Jeshri doesn't know. So I'm sorry. But certainly those are two ways. Okay, Julie. Thank you, Julie, to the rescue. All right, so Jeshri says she'll share links at the end of the session, and Julie just put a link in there, which is a contact RENCI link, and you can use that to send us an email, and somebody will get back to you.
All right, fantastic. Thank you, Ashok. All right, question 2 is for Brian. What types of data files does AppsViz generate from the AdCirc model? Can these products be used for other end users or other applications?
Yeah, so that's a good question. So AdCirc, in particular, outputs its solutions or data in a format called netcdf, and on a spatial representation that's triangles. And so the key issue is to go from that sort of triangular netcdf description of the coastal hazard, for example, into something that can be easily displayed on the web, like a geotiff, or even a shapefile. So the primary endpoints of the data pipeline are formats like GeoTIFF and shapefiles and some other things like that. So that's really what a lot of the containers are doing in APS Viz. And so if if you are interested, if someone's interested in saying, well, I'd like to know what the storm surge looked like, for a hurricane we ran, let's say midsummer, then what we would do is we would find that data set in our big GeoServer database, and we would send a link to it, and you would just download it, and you could suck it directly into some GIS application. So that's essentially what the other groups like North Carolina DOT and the Water Institute are doing, although they're doing it very programmatically and in an automated way. But if we can identify what's interesting, we can always dig it up and make it available somewhere.
Thank you, Brian. All right, this next question is for Suparna. How does Doug find related concepts or studies for a given search term?
Yeah, thanks for that question. That's very interesting. I mean, the core of Doug is to find related concepts, and how we do it is we use the RoboCop knowledge graph that we talked about. And again, RoboCop knowledge graph is an open source knowledge graph that was developed by RENCI, and it draws upon different sources of formalized knowledge. So different biomedical ontologies, such as the Mondo disease ontology, the human phenotype ontology, the Uberon ontology, and that is how it knows that these are biomedical concepts. And it uses a named, and in addition to that, what we do in Doug is we obtain the data dictionaries, which contain all metadata information regarding the variables that are measured or collected in a study. And these data dictionaries are ingested into Doug. And by ingest, we mean that the Doug engine parses through this data dictionary. It finds terms or by terms that are biomedical concepts or synonyms of biomedical concepts, and then it does a named entity recognition. This is what the named entity recognition does, and it stores all this information. And then when a user goes and searches for a term in the in the Doug UI, it knows that, okay, this term is linked to a particular biomedical concept, and there are surrounding the knowledge graph tells me that there are other concepts which are related to it. For example, if you search for heart, which is a human anatomical entity, it would know that heart attack is a concept that is related to heart. And then it will also show you heart attack. And it might know that beta blockers are used for managing certain heart-related concepts, and it would probably show you a term for beta blockers. And because when we got the data dictionaries from different HEAL or non-HEAL studies, like different sources or data repositories, like the information that was ingested into Doug, this contained information regarding what are the variables, what are the biomedical concepts that were studied in different studies. And this is all annotated and stored in Doug. It will know that, okay, if a person is searching for heart or heart attack, then there are like 5 different studies which have looked into heart as a concept or which has looked into heart attack. And that's how this information is presented to the user.
Thank you, Suparna. This next question is for Paul. It sounds like there may be general commercial applications for Fabric. Is that one of the longer term plans, or is it staying within academic research community?
Yeah, so that's a good question as well. The intent here is to do research and try to figure out how to do like the best networking for all of these domain scientists mostly. So for that reason, the NSF makes this available free to almost any academic researcher that has a systems or networking research project, especially targeting domain science. Now, we have a scale. Fabric has the scale to support production environments and potentially something that could be commercialized. But what we want it to be, or what it needs to be, because the NSF pays for it for free, that it needs to be if you have something that you might want to commercialize, you need to make it available for free, do an experiment on Fabric. We can incubate that for a while until you figure out that it works well. But by the time it becomes very popular and you want to maybe sell it or something, we have to like move you off of Fabric and find a good place for you to live forever. But Fabric is a really great spot to like bridge this gap between a research project and a production project, because we can support things at that scale for short periods of time. I hope that answers it.
I think that about covers it. Thanks, Paul. All right, this next question is for Ashok and for me. What are possible career paths at RENCI if I'm not interested in being a researcher? Ashok, do you want to take that one, or do you want me to help out?
I can certainly get started, Hannah, and you can help me. Certainly, there are a number of other career paths that are possible at RENCI besides just being a researcher and advancing that way. One area in which we have an extensive work is in project management and technical project management. So the folks who are in that role are not necessarily researchers in the sense that they do not have a particular domain in which they are doing research, but they are research enablers of the best kind. So they are the ones who are able to run very large multi-institution, multi-investigator project, be able to keep very complicated projects on track and moving forward, be able to provide the necessary training and or the documentation that helps people to advance the project, etc. So that's one possible career path. Another group in which at RENCI in which we have quite a bit of career advancement possibilities is in the communications group, and certainly both Julie and Jayashree, who are on the Zoom, are part of the communications group. And you can help get RENCI's message out, as well as what is happening in the many different research projects that RENCI manages. So Hannah, that's my take on it. You may have a different take and others may, so I'll open it up to you.
Those are two great groups to mention. I'll also mention that we hire a lot of software developers at RENCI. Two of the teams that I work most closely with are mostly made up of our software developers. So if you are interested in programming, if you're a coder, but you're maybe not interested in the science side, there's a lot of work that can be done here, again, in that kind of mid-level of what Ashok was talking about of research enabling. We also have an in-house kind of IT department, our ACES group, and they similarly do a lot of work with network administration and systems administration. So if you have an interest in that as well, there's also a lot that can be done there to, again, help enable researchers and enable these kinds of projects that are happening without necessarily being a researcher yourself. And I think we got a question for Brian. Is AdCirc the only model that the AppsViz infrastructure can deal with?
So no, a lot of it is tailored to AdCirc, sort of at the container levels. The things the supervisor is actually managing are tailored to AdCirc because, again, AdCirc is defined on triangles, and ultimately we want to get to some sort of raster product, and there's some complexity there. However, the supervisor itself, the actual Kubernetes part, doesn't care at all what it's really what it's telling other containers to go do or whatnot. So in fact, we've got another model type running around that I didn't talk about at all, which is a hydraulic model. And that model is described not on triangles, but on squares. And so it's actually a lot easier to deal with squares than triangles for sort of computational and numerical reasons. But so the bottom line is that, in fact, we're going to add a couple of other models probably over the next year. And it will just be another container running around in the supervisor to handle that specific model and turn its output into whatever we need it to be, which again would be in GeoTIFF for the most part. So no, it doesn't ultimately care what the model source is.
Thank you. All right, Suparna, this one is for you. Can you explain a little bit more about where Doug ingests its data or information from?
Yeah, thank you very much, Hannah, for this question, or to the audience for this question. So Doug, essentially, as I talked about, Doug ingest data, or rather data dictionaries, and we do not touch upon any of the actual data. And that is, I think, Doug's unique strength, because we are, by working with data dictionaries or the metadata from the data sets, we avert all the issues related to privacy, related to sharing, data sharing regulations, rules and regulations, or privacy related considerations. Now, where does Doug ingest its data from, or where do we get this data from? So for the HEAL research or the HEAL projects, we ask the HEAL researchers to send us their data dictionaries. And these data dictionaries are files that contain all the variable related information, descriptions of variables, how these variables were measured, what was a questionnaire text, and what are the permissible values for these variables. So this information is contained in the data dictionary, and this is what Doug ingests. And also we look at other sources for data dictionaries, like studies and their data dictionaries. For example, some of you who might be familiar with the biomedical research world would be aware of dbGaP, which is a database for genomes and phenome, and they contain a lot of information about studies, about their data sets, about the data dictionaries associated with this data set, and this is all freely accessible. So Doug, like, in order to find studies that might be related to the HEAL research domain, which is chronic pain or pain management, and OUD, we also look in dbGaP and various other repositories which store biomedical research, and we see like how we can extract data dictionary from these repositories. So that is the sources, different sources from which Doug ingests data.
Thank you, Saparna. Paul, this one is for you. Who can use Fabric, and how much does it cost?
Well, the NSF pays for it. So to the users, it's free. So anyone at an academic institution for sure can use it, as long as they have a problem, a project that fits the goals of Fabric. You probably already, in a way, already have an account, because we use your institutional ID to have you log in. So if you went to the Fabric portal right now and tried to create an account, it would just have you go confirm that you are actually the person you claim to be at your university, and you'd have an account and you can start using it. You would have to become a member of a project. So you'd have to have some professor or research scientist or somebody who leads a project who kind of is responsible for you doing the right thing with the system. But that's it. There's no real cost to it. And, you know, you can even use it for education. So a lot of people use Fabric for teaching, especially networking research, or networking, computer science networking classes use it. So if that's what you're interested in, you can do that too.
Awesome, thank you. Ashok, this one is for you. Does RENCI partner with other UNC schools or departments?
Absolutely. Our biggest strength is our ability to collaborate across departments, across schools. So we have large projects that are ongoing. For example, with the Eshelman School of Pharmacy, certainly with the College of Arts and Sciences, with the School of Public Health, the School of Medicine. So we definitely work across other schools and colleges, as well as other sectors and institutes. So, for example, we have projects with the as Brian mentioned, a lot of the work that he's doing is with the Hazard Center at UNC. We have projects with SHEPS, which is another research center here, with the Highway Safety Research Center. So we collaborate extensively, and that's part of our secret sauce.
It is indeed part of our secret sauce. Thank you, Ashok. All right, this is our last question. It's for Saparna. What are some of the planned enhancements for future features for Doug?
Yeah, this is an excellent question, because, you know, Doug is really a tool that is very much still in development. We were, very proud to release the first official launch of Doug for HEAL like about a month back. And Doug is currently being deployed in Biodata Catalyst, and in future there'll be other deployments of Doug for other projects as well. So there is a lot that we are planning and thinking of including into Doug. For example, so far Doug only works with more of structured data, which is the data dictionary. The plan going forward is like, how can we also include free text, free form text into Doug, like maybe a whole publication, or before that to start off with the summary or the abstract of the publication, like can we get extract keywords or concepts from the abstract and incorporate that into the Doug. So that is something that is in planning. Then we are also thinking of, like, currently Doug, or the deployment of Doug for the HEAL project is it kind of has ingested and shows the relationships between HEAL studies and something called common data elements, which are essentially instruments to measure different biomedical concepts. So we are also considering, in addition to these common data elements, are there other standardized forms of variable descriptions or variables definitions that Doug can ingest and show that representation to the UI, to the user once they use the Doug search UI to search for something. So that's also something in the planning, and we are definitely thinking of how we can use a large language model to enhance the features and capabilities of Doug. So I am very excited to see the direction in which Doug will be evolving, given the projects that we have, given all the technological tools and capabilities that are available to us for enhancing Doug's power.
Many, many exciting things on the landscape. Thank you so much, Suparna. And thank you all for your questions today. Thank you again to our presenters, Drs. Ashok Krishnamurthy, Brian Blanton, Suparna Goswami, and Paul Ruth. We invite everyone here in our audience to reach out today, to learn more, to collaborate, to interact with these projects, and of course, to tell us your thoughts so that we can continue to improve the work that we're doing here at RENCI. In addition to our presenters and panelists, we would like to acknowledge the behind-the-scenes team listed here who worked diligently to bring this webinar to production. Thank you all for your creativity and dedication to helping make science look great. And thank you to our audience for your participation in today's webinar. We hope that you are leaving with a better understanding of how RENCI is addressing changing technology, climates, and environment, health, and networking research. In addition to a recording of today's webinar, this slide deck will be shared, and links to our contact form and newsletter sign up are located in chat. We hope that you will reach out to us to discuss collaboration opportunities, employment opportunities, or general inquiries to learn more about the work that we do. Thank you again, and have a wonderful afternoon, everyone.